Okay, question 3 shows some examples where the second derivative test is inconclusive. And then we're going to have to investigate the graphs to classify the critical points, all right? So part A, we have f of xy is x to the fourth plus y to the fourth. So finding the critical points, we have the x derivative and y derivatives here. Setting those to 0 gives us 0, 0 as a critical point of f. So then, to classify the critical point, right, we use the second derivative test. The xx, the yy derivatives are here. Here's the mixed partial there, it's 0. So d of xy is 144 x squared y squared. Now if I evaluate that at 0, 0, the critical point, I get that d is 0. Okay, so as we discussed, when we looked at the second derivative test, right, that tells us that the test is inconclusive. Okay, so we have to look further. Now, notice here, for this particular function, x to the fourth is non-negative and y to the fourth is non-negative. And since I'm adding these two quantities together, this expression will be as small as possible when both x and y are 0. Okay, so put another way, our surface will have a local, which is also an absolute minimum at the origin. Okay. Now, if you wanted to take it further, right, and look at, say, certain cross-sections of the curve, you know, if I look at, say, the xz trace, well, I'm going to get the equation z is equal to the x to the fourth, right? That's this cross-section right here. In the yz plane, I'm looking at z equals y to the fourth. That's going to be that same curve, but now in the yz plane. And then if I look at the level curves, okay, I'm going to get not circles, but sort of circular-like curves, right, if I set z equal to a constant. But the point, again, is that at 0, 0, I'm actually looking at a minimum. Okay, cool. So now let's look at part B. Our function g of xy is negative the quantity x to the fourth plus y to the fourth. Now the computations are virtually the same as in part A, so I just have them all right here. Again, d is 0. So what do we have here? Well, notice g is just negative f, right? So I'm just going to flip the surface for f upside down, and here I see that at this critical point 0, 0, I have a local, which in this case also happens to be an absolute max. All right, and then for part C, okay, x to the fourth minus y to the fourth is our function h of xy. Okay, so here are the critical points, again, 0, 0, and to classify the critical point, well, d is 0, right? So the second derivative test is inconclusive. What does this surface look like? Well, here I'm going to be a little bit more explicit. Now the xz trace is z equals x to the fourth, so there's that curve. In the yz plane, I'm looking at z is negative y to the fourth, so that looks like this. So now, right, if I were to put those together, I'm actually going to get a saddle-shaped surface, right? So here's the xz view, you see in blue, and then in green would be the yz view. And so, right, I have a saddle point at the origin. Let me bring up a picture on math3d.org. You can see here, right, that this looks kind of like our Pringle chip saddle surface, but because of these fourth powers, things near the origin are extremely flat, right? And it's that extreme flatness that's giving rise to this quantity d equaling 0. In other words, it's so flat that the second derivative is not sensitive enough to detect how things are changing near the origin, okay? But nonetheless, we see we have a saddle point, right? Cool. Well, big takeaway from this again is that in the case when d is 0, it's possible to have a local min, that's part A. It's possible to have a local max, that's part B, and it's possible to have a saddle point. That's why the test is inconclusive. Cool. Well, that does it for this video. See ya next time.